Alright, so today we're going to be looking at evaluating indefinite and definite integrals by using integration by substitution. It's a little bit different than what we did before, but a lot of the same kind of ideas. So it shouldn't be too bad. It's kind of like doing the chain rule when we find derivatives, except for we're doing it in reverse. So these are some steps that we're going to do each time, and then I'll show you how all these work. So we're going to choose a new variable u, and that's going to be our inside of our composite function. So when we had a composite function, we had something along these lines. So for example, we had x squared plus 3 inside of a power of 3/4. That would be like a composite function. In this case, our u would be the x squared plus 3. So then we're going to compute the derivative of u with respect to x. And when we do our integral, we're going to replace all the terms in our original expression with u and du. And we'll see how this all works when we do a couple examples. And then evaluate the resulting integral, which will be just like the ones we've done previously. It'll be one of the ones that we have our antiderivative formulas for already. And then we replace each occurrence of u in the antiderivative with the corresponding expression in x, and then that's our either indefinite integral, or we can then go on with a definite integral and put our a and b values in and use the fundamental theorem of calculus to evaluate. So I think the easiest way to see this is just do several examples. So we're going to evaluate this integral. This is an indefinite integral. So I want you to notice a couple things. Our inside here is this x to the fourth minus 1. So we're going to call that u. So we're going to say u equals x to the fourth plus 1. And then we need to differentiate this with respect to x. So if I do this with respect to x, you'll notice the derivative is 4x cubed. And the only difference now from what we had before is we're going to put a little dx out here because we differentiated it with respect to x. So du is equal to 4x cubed dx. So you might be thinking, well, if I look up here, I can kind of see that there's an x cubed and a dx. So I'm going to have to make that into du. So we can do that really easily, but that 4 has to be taken care of by putting a 1/4 out front. So I put a 1/4 out front, and then if I have 4x cubed, this is the exact same integral that we started with. Except now I've got this is du, and this is u. So when I do this, I don't want to try to integrate with respect to x anymore. I can change this and be an integral of the stuff inside the parentheses, change to u to the negative 2/3 du. Now I can actually do this using the power rule, whereas before with the other stuff I really couldn't do that. So if I go ahead and keep going with my power rule, I've got u, and then I'm going to do negative 2/3 plus 1 over negative 2/3 plus 1. And then I've got to have my c out here because it's an indefinite integral. And if we do that, you'll see that I've got u to the 1/3 over 1/3 plus c. And we have to take care of this 1/3 and this 1/4. So 1/4 divided by a third is equal to 3/4 u to the 1/3 plus c. And we're almost done, because now all I have to do is take this and replace the u. So replace u with x, with our original x plus 4, and that'll be my antiderivative. So this whole thing is actually equal to 3/4 and then I've got the x to the fourth plus 1 to to the 1/3 plus c. And that's my antiderivative. That's my value for my indefinite integral. I'm finished with this problem. We could go ahead and do the chain rule and find the derivative of this, and if you did that, you would see I get my original function underneath my integrand if I do that. So each time we look at these, we're going to be like, okay, I know this is a little bit more complicated. However, I know that sine is the derivative, is in the derivative of the cosine. So my substitution here, u is going to equal the cosine of x. And if I take the derivative of that with respect to x, I get negative sine of x dx. So when I get started on this, I'm going to have to push a negative sign out front to take care of this negative sign. And it ends up becoming the negative integral. And I got the negative sine of x over the square root of cosine of x with the dx out here. So I've got du on top. So this is du. And u is equal to that. So that changes this to the integral of 1 over the square root of u du. Which again, this is going to be a power rule situation because I've got the negative integral of u to the minus 1/2 power du, which we can use our power rule to do. So we've got u, I do negative 1/2 plus 1, and that gives me a positive 1/2 up here, and then I'm going to be divided by a 1/2, and I'm adding c. So really I've got negative 2u to the 1/2 plus c, and I go back and substitute my u value in, which is the cosine of x, and I get negative 2, and the 1/2 power is the square root of the cosine of x plus c. You know, a lot of the same processes that we used in the last few sections to find these integrals, so they're not too terrible. It's mostly just figuring out the correct substitution. So on here we've got x squared, and I've got a cosine of x cubed. So you need to remember what we're looking for when we do this. So I do know an antiderivative of cosine, but I don't know what to do with this x cubed in here. So if I take u as x cubed, though, I know the derivative of that is 3x squared. So that gives me the x squared out here in the front. Alright, so you got to keep in mind when you do these that you'll see a piece of your derivative out front, and that gives you an indication of where to go. So again, I've got a 3 here, so I've got to take care of that when I do a substitution. So I push a 1/3 out front of my original integral, and then I make that 3x squared cosine of x cubed dx. So again, my u is the x, my du is the 3x squared in the dx. So that means I've got 1/3 of the integral of the cosine of u du when I do my substitution. So I substitute this in for the 3x squared in dx. I make that du, and I substitute in the x cubed. Instead of that, I'll write a u down. Now we know how to do this because the integral of the cosine is just the sine of u plus c. So we have that antiderivative formula. That makes it simple. And then I just go back and substitute in my u value that I started with, and I am finished. So again, that makes it a little easier to do. Whenever we have more complicated problems, that's what we kind of have to do. We have to pick what is our substitution. So if you look at this one for a second, you might be like, okay, what had a square root? And if you look back on page 347 in your book with the table, we can see that that actually is an inverse trig function. It didn't have an x on the top though, it had a 1. It didn't have an x to the 4th, it had an x squared. So if we look here, we could think of this x to the 4th as x squared squared, and that means our u value is going to be x squared. And if I do the derivative of that with respect to x, I get 2x. And that helps us out with the x on top, and that gets rid of that x to the 4th on the bottom with the substitution. So again, since I've got that 2 here instead of a 2x, and I don't have a 2x in my original integral, I have to go ahead and put it in there before I do my substitution. So in order to put it in there, I need to have a 1/2 out front. 1/2 of 2 gives me the 1 that I needed. And since constants can be pushed back and forth with an integral sign, it makes it a little bit easier to do. So here we've got this, and again, this top part is now du, and I can do my substitution and change this to 1/2 the integral of 1 over the square root of 1 minus u squared du, which we have a formula for. Our antiderivative of that is just going to be this inverse sign. So I got the 1/2 the inverse sign of u plus c. And then I just got to plug in and substitute this back in. Alright, so that gives me the inverse sign of x squared plus c, and that's my final answer. So again, the key here is picking the right thing to substitute, and that just will come with some practice. Again, we'll see some of these where we have definite integrals. So we start off the exact same way as we did in the last example. Here we're going to make a substitution of u being the stuff inside the parentheses on the bottom, and du, the derivative of that, is going to be 2x dx. So again, if you look at here, you can easily see I've got an x dx on top, and then I've got this stuff. So it makes sense to make u into what's inside. In order to get that pushed out, I need a 1/2 the integral of 2x over this stuff on the bottom, x squared plus 1 squared. And now I can make my substitution. It's 1/2 the integral from -1 to 1 of 1 over u squared du. So now I can integrate with respect to u. I got to remember this is just 1/2 the integral from -1 to 1 of u to the -2nd power, and I use my power rule. And the only thing that's different this time is we've got a definite integral, so I'm doing 1/2, and then I've got my little antiderivative, so I'm adding 1, so that's u to the -1 power over -1, and I'm going from -1 to +1 on that antiderivative. So I'm doing the exact same thing now that we did last section with the fundamental theorem of calculus, and I'm going to change that u back to my x squared plus 1, and we're going to evaluate from my endpoints. So if I put those endpoints in, I get 1/2, and then my first one I've got 1 squared plus 1, so I got -1 over 2, so that's -1/2, minus my other endpoint, my -1. So I get the same thing again because -1 squared is the same as 1 squared, so I get -1/2. That ends up being 0 because -1/2 minus -1/2 is 0. My final answer to this example is 0.
for Alcatraz.
All right, and to our last example here, we've got an integral from pi over 4 to pi over 2 of the cotangent of x. So, we might look at our antiderivative page and say, hey, there's not one of these on there. But I know that cotangent is just cosine of x over sine of x. And we can now do something with that. We got from pi over 4 to pi over 2. So in this case, our u is going to be our sine of x. And our derivative of that is the cosine of x. And then we can actually just use our substitution and make this the integral pi over 4 to pi over 2. And then it's actually just going to be 1 over u du. So anytime you have a 1 over u du, or 1 over x dx, that is your natural log of the absolute value for your antiderivative. And here we're going from, again, pi over 4 to pi over 2. And we just have to put our sine of x back in for u now. Alright, I wrote that a little too big. Alright, and then we're going to do the natural log of the sine of pi over 2 minus the natural log of the sine of pi over 4. And that's where we look at our unit circle again. So if we look at the unit circle, the sine of pi over 2 is 1. And we do the natural log of absolute value of 1 minus the natural log of sine of pi over 4 is the square root of 2 over 2. And as always, this is equal to 0. So my final answer is negative natural log of the absolute value of the square root of 2 over 2. That will be my final answer. Alright, as always, make sure you're asking questions if you don't understand what's going on. Alright.